As researchers with one foot in phonological theory and one foot in electrophysiology, we're extremely interested in whether we can use the tools of electrophysiology to find evidence of abstract linguistic categories like phonemes in patterns of brain activity. A growing body of research has used mismatched negativity in a varying standards paradigm to isolate brain responses, which correspond to phonemes. This paradigm has been used to argue for phonological theories about allophonic variation and featural underspecification in several languages. The underlying assumption in these studies has been that by introducing phonetic variance, recording different speakers, recording different tokens by a single speaker, electronically manipulating phonetic features like formant frequencies or voice onset time, that the auditory system will be unable to make phonetically detailed predictions, and that the ensuing brain responses will reflect only the phoneme category identity, or relevant abstract features like plus or minus voice. We refer to this as the varying standards assumption. We argue that it has not been sufficiently established that the prediction error signal in these cases is wholly categorical and lacks phonetic content. We find studies which observe phonological MMN effects using only a single standard, and at least one study which observed subcategorical phonetic MMN using varying standards, indicating that varying standards may not be either a sufficient or a necessary condition to elicit purely phonemic mismatch effects. To test this varying standards assumption, we measured MMN to a subcategorical VOT contrast using standards which also vary in VOT. Several studies have claimed that the MMN is sensitive to the magnitude of the difference between the standard and deviant, so we compared two experimental conditions, one with standards varying in a high range of VOT, and one with standards varying in a lower range of VOT. We have two predictions. First, because the contrast is subcategorical, we should only observe a mismatch if the auditory prediction contains phonetic information about the standards. If the prediction is purely phonemic, we shouldn't get any mismatch at all. Second, if the auditory prediction is phonemic, then the magnitude of the mismatch should be equivalent in both conditions. But if phonetic information is present in the prediction, we should see a modulation of MMN amplitude correlating with phonetic distance between standards and deviant. This will give us a sense of the phonetic granularity of the auditory prediction. We also introduce a random standards control condition to control for the effects of neuronal refractoriness and gradient perceptual encoding, both of which can contribute to observed MMN effects. By comparing the deviance from the experimental conditions directly to the same stimulus in the control condition, we can isolate the prediction error-related component of the MMN. We had participants listen passively to synthesize syllables with varying VOT while their brain responses were recorded with EEG. Participants completed a categorization task before and after the recording session to make sure their perceptual threshold wouldn't shift after exposure to the experimental stimuli. When we compare standards to deviance, we find a robust MMN at the N2 around 300 milliseconds. We also find an equivalent MMN in all conditions, including the control condition. This was surprising since the random presentation in this condition was designed to prevent any prediction from being made. When we investigate the brain responses to the randomly varying stimuli in the control condition, we see a linear pattern of amplitude in the N2 correlating with VOT. This gradient encoding effect gives the illusion of a mismatch. To control for exactly these kinds of confounds, we also compared the deviance from the experimental conditions to the same stimulus in the control condition. When we perform this comparison, the mismatch almost entirely disappears, but we are left with a small remaining mismatch effect in a late time window, most likely corresponding to a late discriminative negativity. The amplitude of the mismatch is equivalent for both the high and low conditions, meaning we don't see any effect of deviance magnitude, contrary to our expectation. So what does all this tell us? Even when appropriately controlling for refractoriness and gradient encoding, we still find a small but significant mismatch effect to a subcategorical phonetic difference. While we don't see a phonetic distance effect, we still observe a mismatch to the within-category phonetic contrast. So the varying standards assumption may be too strong. The auditory prediction system does still track subcategorical phonetic information at some level of detail, even when that information is varying.